Scientists are among the smartest people on the planet, however they squabble among themselves too, just like the rest of us mere mortals. And the latest is the public spat between Eric Weinstein and Michio Kaku.
Michio Kaku. Get Michio Kaku in here with me. Michio Kaku is out of control. Sean Carroll is covering up for this as well.
Why is Weinstein attacking Kaku? Will Kaku reply to the challenge? Keep watching to find out. Why would two eminent scientists lock horns? String theory. Eric Weinstein is one of the scientists that opposes string theory. However, this gentleman apparently knows his onions when it comes to matters like this. Weinstein is an American hedge fund director and podcast host who has a PhD in mathematical physics from Harvard University. He was the joint managing director for Thiel Capital, Peter Thiel's personal investment firm, from 2013 until 2022. He's also known for coining the term intellectual dark web and being critical of string theory and its proponents. He has a podcast called The Portal where he interviews guests from various fields and discusses topics such as science, technology, culture, and politics. He has also proposed a theory of everything called geometric unity that attempts to unify the fundamental forces of nature and explain the structure of the universe. Weinstein's achievements in science include obtaining a PhD in mathematical physics from Harvard University in 1992 under the supervision of Raoul Bott. His dissertation was on the extension of self-dual Yang-Mills equations across the eighth dimension, proposing a theory of everything called geometric unity, which attempts to unify the fundamental forces of nature and explain the structure of the universe using a new geometric structure involving a larger symmetry group. His theory is the first major challenge to the validity of Albert Einstein's field equations. And if you've heard the term intellectual dark web, Weinstein coined it. He's also remained a prominent voice in the public discourse on science, technology, culture, and politics through his podcast and his appearances on other podcasts such as the Joe Rogan Experience. But what exactly is string theory, and why is Weinstein so mad about it enough to attack Michio Kaku? String theory is the theoretical physics concept that reality is composed of microscopic vibrating strings that are smaller than atoms, electrons, or quarks. According to this hypothesis, as the strings vibrate, twist, and fold, they cause effects in a variety of microscopic dimensions that humans interpret as everything from particle physics to large-scale phenomena like gravity. String theory has been proposed as a theory of everything, a single framework that may integrate general relativity and quantum mechanics, two ideas that underpin nearly all of modern physics. While quantum physics excels at describing the behavior of extremely small objects, and general relativity excels at explaining how very huge events occur in the cosmos, they do not get along. Some scientists believe or thought that string theory could solve the conundrums between the two, solving one of physics' key unsolved problems. String theory's popularity among theoretical physicists fluctuated after it acquired fame in the late 1960s and early 1970s. According to a presentation by California Institute of Technology physicist John Schwartz, widely regarded as one of the inventors of string theory. After innumerable articles, conferences, and dry erase markers, the spectacular breakthrough that many had hoped for appears to be further away than ever. String theory is a set of concepts in theoretical physics in which the fundamental building elements of nature are strings rather than particles, such as the point-like electron. Consider minuscule rubber bands wriggling. String theory is basically a quantum gravity theory that elegantly blends gravity and quantum physics. For nearly a century, physicists have been looking for a theory of quantum gravity. And string theories have also been utilized to answer difficulties in mathematics and other domains of theoretical physics. So who came up with string theory? Well, string theory was found entirely by chance. The now famous Veneziano amplitude was discovered in 1969 by Italian physicist Gabriele Veneziano, who drew down a formula describing the scattering of four strings. Veneziano was attempting to describe the physics of particles such as the proton and neutron rather than strings. From that first formula, though, physicists all over the world worked to unravel string theory in the years that followed. The full picture of string theory has become clearer over the following 50 years. There were several bursts of new ideas and deep insights in the 1970s, 80s, and 90s, and string theory is still an active field with thousands of researchers around the world. Here are some fascinating facts about string theory. String theory predicts 10 total space-time dimensions, but we definitely live in 4, 3 space and 1 time dimension. Fortunately, getting from 10 to 4 is simple. String theory predicts that 6 of the dimensions can be wrapped into a small compact shape. Only a massive, precise experiment like CERN's Massive Hadron Collider would be able to witness these compressed dimensions. String theory is a framework used by physicists to describe how forces that are often thought of on a grand scale, such as gravity, may affect microscopic things such as electrons and protons. Gravity, according to Albert Einstein's general theory of relativity, is a force that warps space-time around heavy objects. It is one of the 4 forces used by physicists to describe nature. Gravity, however, is so weak that it cannot be measured or observed on the scale of a particle, unlike the other forces, electromagnetism, the strong force, and the weak force. Gravity's impacts are only evident and significant on the size of moons, planets, stars, and galaxies. Furthermore, gravity does not appear to exist as a particle in and of itself. Theorists can predict what a gravity particle should look like, but when they try to calculate what happens when 2 such gravitons collide, they get an infinite amount of energy packed into a small space, a sure sign that the maths is wrong. One potential answer derived from nuclear scientists in the 1970s is to abandon the concept of problematic point-like graviton particles. Strings and only strings can clash and rebound with no implication of physically impossible infinities. String theory upends the traditional description of the world by replacing all matter and force particles with a single element, tiny vibrating strings that twist and twirl in intricate ways that resemble particles from our perspective. A string of a certain length striking a specific note may acquire the attributes of a photon, while another string folded and vibrating at a different frequency may assume the function of a quark, and so on. String theory was appealing for its ability to explain so-called fundamental constants, like the mass of an electron, in addition to taming gravity. Theorists hoped that finding the appropriate way to explain the folding and movement of strings would be the next step and that everything else would follow. However, the initial simplicity was offset by unexpected complications. String maths did not function in our familiar 4 dimensions, 3 of space and 1 of time. It required a total of 10 dimensions, 6 of which were visible only from the perspective of the small strings. Similar to how a power line appears as a 1D line to birds flying far overhead but transforms into a 3D cylinder to an ant crawling on the wire. And it's important to note that string theory nowadays is not the same as the string theory of the 1960s and 70s, and researchers argue on whether it is still the best candidate for a theory of everything with adjustments or whether theorists should forsake it in favor of other topics. So why is string theory still relevant today? Whether or not string theory may ever be transformed into a theory of everything, its legacy as a fruitful research program may be secure on mathematical grounds alone. When Witten and colleagues demonstrated that the 5-string theories were shadows of a single-parent theory, they emphasized links known as dualities, which have proven to be a significant contribution to mathematics and physics. Dualities enable mathematicians to translate from one discipline of mathematics to another, tackling problems that are intractable in one context with computations performed in the other, as in geometry and number theory. Other dualities have aided in overcoming obstacles in quantum computing. However, it's unclear if string theory's capacity to light the black web connecting diverse areas of maths is an indication of its potential or just a lucky coincidence. Nevertheless, it is clear that the theory remains a viable subject of research. So why does Weinstein oppose string theory? Well, one of the reasons is that he believes it is not falsifiable, meaning that it cannot be tested or disproved by experiments. He argues that string theory makes too many arbitrary assumptions and predictions that are either too vague or too far beyond the reach of current technology to be verified. But why do scientists believe that every theory must be falsifiable? Well, there are several reasons for this. First, falsifiability helps us to avoid confirmation bias, which is the tendency to look for evidence that supports our beliefs and ignore evidence that contradicts them. Confirmation bias can lead us to accept false or misleading theories and reject better ones. By requiring that our theories can be falsified, we force ourselves to confront the possibility that we are wrong and to look for disconfirming evidence. Secondly, falsifiability encourages us to be creative and innovative in our scientific inquiry. If our theories can be falsified, we have to constantly come up with new hypotheses and experiments to test them. This stimulates our curiosity and imagination and leads us to discover new facts and phenomena. Falsifiability also fosters healthy competition and collaboration among scientists who challenge each other's theories and try to find better explanations. Third, falsifiability ensures that our theories are consistent with reality and useful for making predictions and solving problems. If our theories can be falsified, we have to make sure that they match the observations and data that we have. We also have to make sure that they can make accurate and testable predictions about future events and outcomes. Falsifiability helps us to weed out theories that are vague, contradictory, or irrelevant, and to keep only those that are clear, coherent, and applicable. And Weinstein also claims that string theory has no explanatory power, meaning that it does not provide any insight or understanding of the physical phenomena it purports to describe. He says that string theory is more like a mathematical game than a scientific theory, and that it's become a dogma that stifles creativity and innovation in physics. Another reason why Weinstein opposes string theory is that he thinks it is incompatible with his own theory of geometric unity, which he developed as part of his doctoral dissertation. Geometric unity is a radical proposal that attempts to explain all the fundamental forces and particles of nature using only geometry and symmetry principles. Weinstein claims that geometric unity is simpler, more elegant, and more predictive than string theory, and that it can account for some of the mysteries and anomalies that string theory cannot. He also says that geometric unity is based on empirical evidence and logical reasoning, unlike string theory, which he considers to be based on speculation and wishful thinking. Weinstein's geometric unity theory is a bold and ambitious attempt to unify physics and mathematics in a single framework. The theory proposes that our four-dimensional space-time is embedded in a 14-dimensional space called the observerse, which contains all possible observers and their measurements. The observerse is endowed with a structure called a gauge connection, which encodes the laws of physics and allows for transformations between different observers. The theory also introduces a new geometric object called the twistor, which is a complex valued function on the observerse which captures the quantum nature of reality. The theory claims that many of the fundamental concepts and constants of physics, such as mass, charge, spin, and the fine structure constant, can be derived from the geometry of the observerse and the twistor. The theory also predicts new phenomena and particles, such as a dark energy field that permeates the observerse and a dark matter particle that is a bound state of two twistors. The theory also offers a new perspective on gravity, which is seen as a manifestation of the curvature of the observerse. It's important to note, though, that Weinstein's theory is still in its early stages of development and faces many challenges and open questions. For example, how to test the theory experimentally, how to relate it to existing theories such as general relativity and quantum field theory, and how to resolve some of the mathematical inconsistencies and ambiguities that arise in the formulation of the theory. The theory also requires a high level of mathematical sophistication and abstraction, which makes it difficult to communicate and understand for many physicists and laypeople. Nevertheless, the theory is a remarkable example of creative thinking and original vision in physics and mathematics. The theory aims to reveal the hidden beauty and simplicity of nature and to uncover the deep connections between different branches of knowledge. What's more, the theory also inspires new questions and directions for further research and exploration. The theory is a testament to Eric Weinstein's genius and courage and his passion for finding the ultimate truth about reality. Now, a third reason why Weinstein opposes string theory is that he believes it is a distraction from the real problems and challenges facing physics today. He argues that string theory has diverted attention and resources from other, more promising and fruitful areas of research, such as quantum gravity, dark matter, dark energy, and the origin of the universe. He also warns that string theory has created a culture of elitism and conformity in physics where dissenting voices are marginalized and ignored. He says that physics needs more diversity and openness, not more orthodoxy and dogmatism. These are some of the main reasons why Eric Weinstein opposes string theory, and he is not alone in his criticism, as many other physicists have also expressed their doubts and reservations about string theory. However, he is one of the most outspoken and controversial critics of string theory, and he has challenged some of the most influential and respected figures in the field. He has also proposed an alternative vision for physics which he hopes will inspire a new generation of physicists to explore new possibilities and discover new truths.